go over, so today we're going to go over chapter 9, which is about complex numbers. And we're going to start with what is complex number. So complex number or imaginary number, you're going to get when you take square root of negative number. Okay? So square root, everybody know what is square root? Square root of number, it's a number which multiply by itself, give you the number inside the radical. And so when you have square root of negative, this is what you're actually doing. If you have square root of negative here, 49, you're going to represent it like square root of 49 times square root of negative 1. And this negative 1, square root of negative 1, is the imaginary unit, which is the letter lowercase I. And square root of negative 1 equals I. And this imaginary unit helps us to represent even numbers when they're square root of negative. Because if you put in your calculator square root of negative, it's going to give you domain error, right? So in order to calculate that, if you define, so the definition of imaginary unit is I, the letter I, it's a square root of negative 1. And then the complex number is going to be represented in this form, a plus bi. A and b are real numbers, okay? A is called real component, and b is called imaginary component, because it's connected with the I, okay? So that's the definition of complex numbers. So now, here we're going to do some operations with complex numbers. So the standard form looks like a plus bi. So this is standard form, also it's called rectangular form of complex numbers. So first operation, we're going to talk about when two numbers are equal. They equal when they have the same real component. So when a is equal a, c, and when they have imaginary component the same. Okay, so that's when the complex numbers are equals. Okay, so you kind of compare the real component and you compare the imaginary component, or you compare the number with no I and number with I. Okay, now what is the power of imaginary unit? So this is kind of before do operations. The power of I. So if you have I, which is square root of negative 1, right? I to the first power is 1, I, okay? I to the 0, anything with power 0 is 1, so I to the 0 is 1. I square is negative 1, and I cube is negative I, okay? So this, the first 4 exponents, we kind of memorize or kind of look them like a given. It's given. A to the 0 is 1 because anything to power 0, it's always 1. I to the first is I, obviously, right? Power 1 is kind of, you don't have to put it there, okay? It's invisible. I square, how you get I square is negative 1. Remember, I, it's a square root of negative 1. Now, if I square both sides, so I'm going to square this side, and I'm going to do exponent 2 in the other side. So I square become square and square root cancel, become negative 1. That's how you get that. Okay? And the other operation, you have I cube. How you get I cube? I cube is I square times I, right? So now I square is negative 1. And that's how you get negative I. Okay? So we're going to assume that we know these 4 is a given. These 4 exponent for I are given. Now, for any other exponent power of n, we're going to find what is actually, it's going to be one of these 4. And this is how you do it. You're going to divide by 4. So I'm going to give you like a rule. You divide by 4 always. Okay? So if I want to do let's look at this example. I with exponent 117. So what you're doing, you divide 117 divided by 4 is going to be 29 with remainder 1. So that's why you represent 117 is I, 4 times 29 and plus 1. See here, you multiply these two numbers and you add in the 1 because 1 is the remainder. Okay, so now I to the 4 is always 1 because it's I squared times I squared, which is negative 1 times negative 1 is positive 1. So I'm going to put that here also in the what is given. I to the 4 is 1. Okay? So I know I to the 4 is 1. So that's how you get 1. And then to the power 29 times I. 120 power is 1. So this is kind of disappear. So that's why you get the answer is I. Everybody understanding that? Any questions?
So I-29, can you repeat what you said about that?
Yes, so we have I to the 4 and then to times 29. So I to the 4 is 1. 1 to the 29 power is 1 because 1 with any exponent is 1. So that's why I just cross it out, disappear. It's not like 1I. 1 times I is I. Yes?
Yes, got it.
Okay. Okay, any other questions? Okay, let's do the next one, example 2. We have I to the 75. So we're going to divide 75 by 4. And that's going to give me, what is that? 4. Hold on, let's do that. 75 divided by 4 is 18. 18 times 4 is 72. And the remainder 3, right? Okay? Or technically what they did here, they represent 75 is 72 plus 3. This 72 plus 3. And 72 is 4, and then 4 times 18. So here 4 times 18 is 72. And then you have I cubed. So now I to the 4 is 1. 1 to the 18 is also 1, right? And then I cubed, looking at I cubed up here, is negative I. Okay? And I to the 18 is disappear, so the answer is negative 1, negative I. Everybody understand that? So I can do more examples. Yes, you guys want to do another example? Just make an example.
Yes.
Let's do another one. So let's say what is I? Yes?
I was going to ask, can you go back to page 4?
Yes.
I just wanted to see how you got the I to the 4 times 18.
Because when you divide 75 by 4, that's going to be 18 with remainder 3. So 4 times 18 plus 3 is 75. So you're kind of breaking down 75 is 4 times 18 plus 3. Make sense?
Okay, thanks.
You're welcome. So we're going to do another example. Give me a number. I to what exponent? Just pick a number. Come on, nobody have a number?
38.
38, thank you. Is that from the text or no? I hope
No,
not.
ma'am.
Okay.
I that out of my head.
Good, yes, thank you. So I to the 38. So what you're going to do, you're going to start dividing 38 by 4, right? So you can just divide 38. It's going to be 9 times 4 is what? 36, right? And remainder is 2, right? So technically you're breaking down 38 is 4 times 9 plus 2, okay? So that's why 38 is going to be I to the 4 and then to the 9 times I square. Make sense? And then I to the 4, you already know it's 1, right? So it's going to be 1 to the 9 times, what is I square? Remember what is I square? Do you guys remember?
Negative 1.
Negative 1.
Negative 1, that's right. If you forget, look here, negative 1. And then 1 to the 9 is 1. So my answer is negative 1. Okay? Everybody understand that? Okay? You want another one or are you good with this?
Wait, quick question. Okay, so
Yes.
I'm with you until you got to the 1 to the 9th power.
Okay, 1 to the 9 power, like 1 with any power is 1. Because it doesn't matter how much you multiply 1, 1, 1, 1, 1, 1. 1,000 times, million times, it's 1. Okay? So if you have 1 times negative 1, what is that? Negative 1, right? Positive 1 times negative 1 is negative 1. Okay? Make sense?
So did you bring the 9 over?
No, 9 disappear because 1 with any power, it doesn't matter if it's 500, if it's 9, if it's 7, if it's negative, whatever it is, it's going to be 1. So the answer for 1 to the 9 is just 1. Okay? Does that make sense or no? Okay, I see thumbs up. Okay, thank you. Okay, so do you guys want another example or are we good with this? Okay, so we're going to go to the next slide then. The next one is about connection between the complex number in matrices. So here we have, we represent the complex number with matrices. The I matrix, you remember the unit matrix, it's 1, 0, 0, 1. We did this in algebra where 1 is in the diagonal. Now, if you have 1 and 1 like this in diagonal, that's going to be the letter I. Okay, that's standard, that's how it is. And then calculating I square is going to be like here, we're using the order of operations with the operation with matrices. When you multiply row by column, we did this in algebra. We're not going to do that now, so I'm kind of skipping it through. So when you multiply, you're going to get this matrix, and this matrix you have negative and negative, so you're going to factor out negative 1, and you're going to be negative 1, which is exactly what you get, okay? So I'm going to kind of go explain that you have connection between the complex number in matrices. We're not going to do a lot with that, okay? Then we have principal square root. Is it similar in the case of complex numbers? Yes. So when you have to take square root of imaginary numbers, pretty much if you have square root of negative, you have to kind of isolate the I and then just take square root of it. Okay, makes sense? So here we're going to start with the operations. So these are the operations with complex numbers. The sum of two numbers, complex numbers, it's pretty much adding the real component and adding the imaginary component. Excuse me. So if I add, looking at example 1, I'm going to add 5 plus 7i and 8 minus 2i. So I'm adding 5 plus 8, which is 13. And then I'm going to add the numbers with I. I'm going to add 7i, and minus 2i is going to give me 5i. And here you have it step by step. You make it in groups and all that, but this is actually what you're doing. You're combining number with number, I with I. Okay? It's like combining like terms. Okay? Everybody understand that? So adding complex numbers is really easy. You just add the real component and you also add the imaginary component. In example 2, here you add in 5 plus negative 5, give me 0. And also you're going to add negative 7i and plus 3i give me negative 4i. And then because 0 it's just 0, doesn't matter. You're going to just get the answer. It's going to be negative 4i. Everybody understand how to add complex numbers? Okay. The next one is going to be subtraction or difference of two complex numbers. So here we're doing pretty much the same. But when you have minus, you're going to subtract 10 minus 6, which is what? 4, right? And you're also going to subtract negative 3 minus 2i. Now, when you subtract minus, be careful, minus become positive 2. So that's why it's better to kind of break it down. Take off the parentheses, so it's better to do it this way. I'm going to write it here. Copy the first one, 10 minus 3i, and then distribute this negative. So it's going to be minus 6, and then minus and minus is going to be plus 2i. So it's always better do the parentheses first, distribute the positive, the minus. If it's positive, the parentheses doesn't matter. But here, because you have minus, distribute it, that change the signs inside the parentheses, and then combine 10 minus 6 is 4, and then negative 3 plus 2 is negative invisible 1i. Okay? Everybody understand that? And I'm going to do examples after I just go over the basic operations. Okay, the next operation is multiplication. So how you multiply complex numbers. When you multiply, you're going to do the multiply, you're going to FOIL. So multiply 9 minus 3i, 5 plus 7i. You multiply in first and first, multiplying the outside. So you have 9 times 5 is 45. 9 times 7 is 63i. Then you're going to do the inside. So this is F, O. And then you do the inside. So this is I. And then you're doing the last. Okay? You're doing FOIL. And then after that, you're going to replace I squared. What is I squared? Do you guys remember what is I squared?
-1.
Good job, -1. So I'm going to replace I squared with -1, and -21 times -1 give me positive 21, right? And then you're going to combine I and I, and also you're going to combine 45 plus 21. And that's going to give me 66 plus 48i. So the steps are you're going to FOIL. You're going to, second step, replace I squared with -1. And then combine I with I, number with number. You got it? Everybody good so far? Okay, so the next operation we're going to talk about is division of two complex numbers. But before you divide, we're going to talk about conjugates. So what are conjugate numbers? So conjugate numbers are numbers we're using when you divide two complex numbers. And the conjugate means using the same real and imaginary component with opposite sign in the middle. So for a plus b, I, the conjugate is a minus bi. So you're just changing the sign between those two numbers, those two components. Okay? So that's what conjugate means. Okay? So we have two conjugate numbers. Why you need conjugates? Because when the property for conjugates, if you multiply two conjugate numbers, the answer is going to be a real number. So let me explain that. So I'm going to give you a number and you're going to give me a conjugate of it. So if I have, let's say the number is 1 plus 2i. What is conjugate of 1 plus 2i? 1 minus 2i, that's right, 1 minus 2i. So now we know how to multiply conjugate numbers. So let's multiply 1 plus 2i, 1 minus 2i, and see what you're going to get. So when you multiply two numbers complex, you're going to FOIL, right? This time this, and then the inside and the last, right? So we're multiplying. 1 times 1 is 1. I'm going to continue here, 1. Then 1 times negative 2i is negative 2i. And then the inside, the 1 times 2i is 2i plus 2i. And then I'm going to get negative 4i squared. So when you do that, see 2i and negative 2i cancel out. Okay? And then the next step was replace. After you FOIL, you're going to replace I squared with what? Negative 1, right? Because I squared is negative 1. So we're going to get 1, 2i and 2i cancel out. And then I have negative 4 times negative 1, which is positive 4. So what is 1 plus 4? It's just 5. It's a real number. Okay? So that's why you're using conjugate numbers. Because when you multiply two conjugates, you're going to get a real number. No more I. So that's the idea behind dividing complex numbers. So when you divide, see here we have example. We have 11 minus 6i over 5i. See, technically you're dividing 1 minus 6i. The fraction, the line means division, right? So you're dividing by 5i. So this here actually means you have 11 minus 6i. This complex number, you're dividing by 5i, right? That's what fraction means. Fraction means division. So in order to divide those two, I need to get rid of this imaginary number. So that's why you multiply. When you divide two complex numbers, you multiply by conjugate of the denominator. So conjugate of 5i is negative 5i. And you multiply up and down, so you don't change the fraction. You multiply up and down the numerator and denominator by the conjugate of the denominator. And when you do that, you're going to have no I in the denominator, which is actually a real number, right? So when you do that, you're going to multiply the top. So multiply this times negative 5i, and you multiply in the bottom 5i times negative 5i. So when you distribute, 11 times negative 5i is negative 55i. And then when you multiply the other two, negative times negative, it's positive. 6 times 5 is 30. And then you have the I squared. Now this I squared you're going to replace with negative 1, right? So that's how you get negative 55i minus 30, because positive and negative 1 give me negative 30. Now what's happening in the bottom? 5i times negative 5i is negative 25i squared. Now this I squared is also negative 1. Everywhere you see I squared, that's negative 1. Negative times negative give me 25i. So now, this is just one number. How I know it's one number? I can split this fraction. I can write negative 55i and negative 30, right? And both of those are over 25, right? So you split in the fraction. You put negative 55i over 25 minus 30 over 25. So when you split the fraction, you see you have exactly the standard form of complex number. Number with I and number with no I, right? So when you divide those two numbers, you're going to get one complex number, which is going to have imaginary component and also real component. Okay, everybody understanding this? Yes, okay. So do you guys want more examples of the operations, or we can go to the next one? You want more examples? Yes or no?
I'm okay to keep going.
Okay. Everybody okay? Okay. So we're going to the next one, which is 11th slide. So here we're going to talk about Argon diagram. And Argon diagram is a graphical representation of complex numbers. Okay. So what that means, how you represent complex numbers. So this Argon diagram actually gives me where the complex numbers are, right? So you know, and probably I talk about that in algebra, but I didn't always go Argon diagram. I talk about where the complex numbers are. So here we have, if I have a number line, you know, all the numbers you know so far, they're in the number line. You have 0, you have 1 and 2 and so on, right? And then you have negative numbers, negative 1, negative 2 and so on, right? So the numbers in the number line continue to infinity, and the left side go to negative infinity, right? Everybody familiar with the number line? Then between the integer numbers, you have a decimal numbers, right? So there are many decimal between the whole numbers, between the integer numbers. So now where the complex numbers are. So the complex numbers are technically like a, in quote, two-dimensional numbers, because the real numbers, so all these are real numbers. Okay, so the real numbers, they're in this real number line, so they're one-dimensional, one line. Now when you have complex numbers, they're everywhere around. They're like outside of this line, so they're on this plane. The plane is two-dimensional, right? Okay, so now how they look like, where they are. So if you pretend that you have, this is your real component, and it's like in rectangular coordinate system, you have the y, x and y coordinate system, you know that, right? So if you have, this is your real axis, and if you do look at the y-axis like imaginary axis, so if you look the real and imaginary axes, like similar like x and y axis in the rectangular coordinate system, you can see that any point can be represented with real and imaginary component. Okay, so let me show you how. So if I pick a point, let's say I pick this point here. And this point has coordinates in x and y coordinate is going to be x is 1, y is 2, right? So this point has coordinates 1 and 2, and this point represents the imaginary number 1 plus 2i. So this is the point here. Now, if I pick another point, let's pick this point here. This point has coordinates going to the x and going to the y, right? Going to the real and imaginary axis. So it has negative 2 real and 1 imaginary. So this point is the graphical representation of the number negative 2 plus 1i. Okay? Now, if I pick, let's say, this point here at 1 in the real, what are the coordinates for this point? The coordinates are 1 and 0, right? So this point, the orange one, is going to be a representation of the complex number 1 plus 0 imaginary. Okay? So that means all the real numbers you already know. You already know the real numbers. 1, 0, 3, 5, 2.5. You know where exactly they're in the number line. So all these real numbers you already know and you deal with them all your life, they're also complex numbers because they have imaginary component 0. Make sense? So if you look at the real numbers, like a set of the real numbers, the imaginary or the complex numbers, they include the real numbers. So these are the imaginary numbers, okay? Or complex numbers also. They're also called complex numbers. I'm going to use complex. Okay, so this is the symbol for complex number, and this is the symbol for real, like a double line here for the R. Okay, so the set of real numbers is included in the set of the complex numbers. Okay? Okay, so let's say I pick another one. I'm just going to show one more point. So let's pick another point which is going to be over here in the y-axis, in the imaginary axis. So if I pick this point here, the green one, which is like 2 steps away, so you have -1, -2, it's 2 steps away from the 0 below. So this green point is the imaginary or the complex number -2i. And you can just put invisible 0 minus 2i. Okay, so everybody understand how the complex numbers are represented? They're like 2-dimensional numbers. They're represented with real component, real axis, and imaginary axis. And any point on the plane could be represented with imaginary number. Now, let me ask you a question. Do you guys think that they are 3-dimensional numbers? What do you think?
Yeah. Z.
Yeah, absolutely.
Absolutely.
Yeah. How about
There has to
4-dimensional?
be. I mean, gravity is represented in, well, 4 dimensions, but
Yeah, you can have 4. You can have 5 dimension. You can have infinity dimension, right? So, so the imaginary numbers pretty much open your imagination, right? Okay? Expand your thinking process. Like looking in the different way of everything going on around you, okay? So now let's look at the example they give us here. They give us the representation of the number 5 plus 3i. So this is how you're going to represent that number. So you're going to go 5 to the x-axis, and you're going to go imaginary axis, and you're going to go 3 to the imaginary axis, and whatever they cross, that's the point. And then you're going to connect it like an arrow from the 0. So this is the representation of imaginary number 5 plus 3i. Okay? Everybody understand that? It's cool, right? Okay, let's look at another example. So here we have a graphical representation of product of 2 numbers. So here we have, they give us to calculate the product of 2 plus I and also multiply by I. So we're going to graph the 2 plus I. So 2 plus I is the green one in the graph. I is the red one in the graph. And when I multiply those two numbers, I'm going to get -1 plus 2i, which is the black error on the graph. And in order to do that, to get the graphical representation, I have to multiply the way you just multiply. Just distribute the I, so that's going to give me what? So when I distribute, I'm going to get 2i plus I squared. And I know I squared is already -1 plus 2i. Just keep the 2i. And usually we write the real component in front, the imaginary component in the end. This is kind of unspoken rule. So when you have a complex number, usually, I mean, that's kind of rule we are following. The real component goes first and then the I goes in the end. Okay? So that's how you do the Argon diagram. Any questions so far? Okay, so then we're gonna go continue with polar coordinates. So now you know the real and the imaginary components of the complex numbers. We're talking about polar form of the complex number. So this is another way of representing a polar numbers, which is connected to the polar coordinate system. And we're going to use this in next week when we talk about vectors. And we're going to talk about polar and rectangular coordinate system of vectors. So polar and rectangular coordinate system, they are just two different ways of representing any point on the plane and in the plane. Okay, so this is what you have. So we're gonna talk about polar and rectangular. So this is, I'm gonna give you a graph. So when you have a rectangular, you using x and y, right? This is what you're using, x and y, like two perpendicular axes which cross at the origin, which is 0, right? So this is the rectangular. Now the polar coordinate, it's connected with, for polar we need only the x-axis starting from the 0, and we also, so this is the polar coordinate is connected with start from the 0, the x-axis, and you also, let's say if I pick this point, I'm gonna connect that point with the center, with the 0, 0, and I'm gonna measure the distance. I'm gonna measure the angle with the x-axis. I'm gonna measure, this is angle theta, and also I'm gonna measure the distance from 0. So this is called r. So we have r, we have theta. R is called the modulus of the complex number, and theta is called the argument of the complex number. So r is the distance from that point you want to find the coordinates, from the point to the 0, 0, right? So this is the 0 of the coordinate system for the polar coordinate system. And theta is the angle we have with the x-axis. Okay? So this is your x-axis. Okay, so this is how the polar coordinates looks like. Now for rectangular, I'm just going to remind you, if I have any point, let's say I have the same point, the rectangular is going to be connecting the point with the x-axis and the point with the y-axis. So if I have a rectangular coordinate system, I'm going to measure the distance. So this is x and this is y. So that's why the rectangular is represented with, any point is represented with x and y. With the polar, any point is represented with r and the angle theta. So these are the two different ways of representing any point. And this is what they mean. So we have rectangular, we have x and y with rectangular coordinate system, and the polar coordinate system, you have r and the theta. R is the distance from the 0, and theta is the angle with the x-axis. So everybody understand this? Now I'm going to give you the formula and everything, how to go from polar to rectangular and everything, but just to get the idea, what is the difference between those two coordinate systems? Any questions so far? Okay, then we're going to the formulas. So here we have converting from rectangular to polar. So when you go to polar, which means you have x and y given, so the rectangular is x and y, and the polar is r and theta, right? So this is the formula. If I want to find r, I'm using this formula. Okay, in this case, instead of x and y, they're using a and b. So let's just be consistent with what they have here. So let's say rectangular is a and b, so the coordinates a and b, which is going back here to my graph, so my picture. So let's change that. We have a and b. So the distance from the x-axis is a, and b. Okay, so let's be consistent with the PowerPoint. Okay, so if I want to find r, I'm going to do square root of, here they're using the distance formula, so they just explain how we do that, but this is what you have to use. Square root of a squared plus b squared. Okay, and then these are the formulas to calculate the theta, the angle. Okay, so here this is kind of pre-calculus, and I'll show you how to do that. So depends where your point is. So let's say you have a point into, so this is your x-axis, this is the origin, and let's say you have a point here in the second quadrant. So when you connect it with the zero, this is r, right? And the angle with the x-axis is going to be, this is the angle theta. Okay, so if the angle is in second quadrant, which is, so I'm going to write here first quadrant, the angle is between, and how you know which quadrant you are? I mean, from the coordinates, right? Let me explain here. So if I have, these are the quadrants, you have first quadrant, second, third, and fourth. Okay, and in all of these quadrants we have in the first quadrant we have positive A and positive B. In second quadrant you have negative A and positive B. In third quadrant both of those are negative, and fourth quadrant you have positive X and negative Y. Okay, so this is how the coordinates are in the four quadrants. So that's how you know which quadrant you are. Just looking at the point, we're going to do example, but looking at the point you can see which quadrant you are. And then when you calculate the angle, you're going to use the tangent inverse formula. So this is formula from pre-calculus, and look it like a function. And the function, you're going to put it in the calculator. So I'm going to show you. So if I want to do the formula, the function, you're going to use symbol up, and you're going to just put it exactly like that. So if you go to symbol up, you're going to just enter tangent with exponent -1. So you're going to put exactly what it says here. So you're going to put tangent with exponent -1, and then you're going to put your two numbers, and it's going to give you the answer. Okay? And then you're going to add pi, or 2 pi, depends which quadrant you are. Okay? Now we're going to work with degrees. So pi is radians. Pi is, 3.14, but we're going to work with degree. So instead of adding 150 here, instead of adding pi, you're going to get the answer in degree, and you're going to add 180 degree. And this is the same 180 degree. And 2 pi is going to be 360 degree. So we're not using radians, we're going to use, yes, we're not using radians, we're going to use degree. Okay? And the calculator is going to give you the answer. So we're going to look at example. We're going to practice this, okay? So, so that's how you're going to change it. If you need to find the polar coordinate system, you're just going to use this formula to find the r. And then if you need to find the theta, depends which quadrant you are, you're going to use the tangent inverse, okay? And let's do example. So here they give me, we need to find the polar representation of -3 plus 5i. So these are the coordinates. This is A, -3 is A, and 5 is my B, right? Now, which quadrant we are? We are in second quadrant because, going back here, we have negative and positive. It's second quadrant, right? Let me make this. So positive and positive first, negative and negative third, positive and negative fourth. Okay? So we know in second quadrant. So you're going to find the R. For R, technically it doesn't matter which quadrant you are, only for the angle, for theta. So you're going to do a squared plus b squared, right? So a squared -3 times -3 is 9. 5 times 5 is 25. When you add it, you get square root of -34. That's the r. That's the distance from 0. Now, finding theta, you're going to do this. You're going to put tangent inverse in the calculator. So in the calculator, I'm going to do it. So I need to do tangent inverse b over a, which is, so in the calculator, I'm going to put it here so I can see it. On the calculator, I have to put tangent inverse, that's what it's called, tangent -1, of 5 over -3. That's what I need to put in my calculator in symbol up. Okay? So I'm going to go there and I'm going to enter that. So I'm going to put tan, just type it in. Then you're going to go to the exponent, you're going to put -1. And then down here I can just put parentheses 5 divided by -3. And then the calculator is going to give me the degree. And this is what I have. I have it in degree and I have it in radians also. So it's -59.04 degree. So that's exactly what I have here, -59.03. 04, depends how they round it. And then you're going to add 180. And this is my angle, 120.97 degree. Okay? And what that means this imaginary number in rectangular coordinate system is going to be the same, represented with the same point, represented with polar coordinate system, square root of 34 with angle 120.97 degree. Okay? So that's how you do rectangular to polar. Okay, so the next one is going from polar to rectangular. So going backwards, the other way. So if I want to change polar to rectangular, these are the formulas you're going to use. Okay? So if I have polar now, so this is given, r and theta is given, and I have to find a and b. You're just going to plug it here and then you're going to use the calculator. Again, cosine and sine, they're pre-calculus functions, and you're just going to type it in the calculator like in your keyboard. You're going to type it in COS, okay? Okay? So this sine and cosine, so these are the two functions we're going to use. They're pre-calculus functions. And I'm not going to go in detail. We're just going to plug it in exactly the way they are. Okay? Here we have, the next one is going over when you have exponents. So this is why you need the rectangular. This is why you need the polar form, because when you have exponents, number with exponents, with higher exponent, it's easier to go to polar and then do the exponent. Okay, so that's why you have it here, and I'm not going to go in details in this because you don't have it in your actual quiz, but so that's why you need the two different forms, because one form is easy for adding, subtracting, multiplying, and dividing. The other form is easy if you have exponents. Okay, and also there are some more applications. So we have polar form, and polar form it's easier, and here you have the Morgan theorem, which also deal with exponents. We're gonna just kind of skip that. And then one application of imaginary complex number is when you have the electrical impedance, when you use it in electrical impedance, using that, and when you multiply, and here you have some more applications. Fractal image generation, when you talk about fractals. So fractals are really cool geometrical construction, which also, when you divide it in parts, they are actually the same copy of the original, but just kind of reduced scale. Okay, and this is why also you have in fractals, which are geometrical constructions, you have also use of complex numbers. Okay, so this is what you have for this week. You have operations with complex numbers. We have complex numbers in rectangular and also polar form. The trigonometric form, I didn't go in details. We're not having that in for this week. And then we have the basic operations with complex numbers. Okay, so that's what we have for this week.